architecture. And you can find also my email address if you are interested in contact me. Thank you again.
Thank you very much. We have your email address. Thanks. If people they want to ask you questions, they send to you by email. Thank you.
Okay. Thank you very much.
We go to the last but not the least presentation of the session.
Good afternoon, everyone. I am Ravikant Singh. I am a PhD research scholar at IIT Patna, and I am presenting this paper along with Dr. Avik Samanta. And the topic of my presentation is performance of light gauge cold form steel structural members subjected to non-uniform fire. Here is the typical outline of my presentation. We will start with introduction, development of the FE models, parametric study. We will finish up with the results and discussion and references. Starting with the introduction, cold form steel finds its application in wide range of fields such as industrial, commercial, and agricultural spaces, roof and wall system, steel racks, plane and space trusses. Also recently, automobile and space industry is also very much interested in the use of cold form steel structures. Now, coming down to the temperature part, cold form steel are very usually thermally insulated. Also, sometimes forced cooling on the member can introduce huge amount of thermal gradient on these members. For example, this is the results of the work by Fen and Wang in 2003. Here we can see huge amount of thermal gradient between the top and bottom fringes of the cold form steel sections. Thus, my research particularly focuses on the study of cold form steel flexural members under non-uniform fire for simply supported boundary conditions under 4-point loading setup. Now, here is the development of my FEM model. For that part, first I have performed the eigenvalue buckling analysis, and second part I have performed the non-linear static analysis. The imperfection shape was imported from the first mode shape of the eigenvalue buckling analysis, and in which was imported in the second stage of the simulation, FE simulation. The non-linear analysis was further performed in two stages. First, with the loading, starting with the loading stage, and second is the heating step. Now, in the initial, that is the loading step, we will apply the initial applied load level on the member. Once that particular state of load is achieved on the member, then the temperature on the member is increased till 1800 seconds. And here is the validation work. I have validated my models with the existing experimental and numerical work by Liu and Yin and Long. For that, the thermal temperature, what is considered on the member, is highlighted here. Here, the top of the flange as well as bottom flange of the member, along with the temperature of the web, is highlighted in this figure. This is the validation results. Here, the solid line represents my developed model. However, the dashed and dotted lines are the numerical and experimental results available in the literature. Here, in the horizontal axis, I have presented temperature. On the vertical axis, there is the vertical displacement recorded at the center of the cross-section beam. And here, the axial reaction force, whatever generated in the beam, is plotted with the temperature recorded on the member. Both of these results indicate the fact that the models were very much suitable for the further studies. Now, further we proceeded with the parametric study. For the parametric study, I have considered three different beams, that is B1, B2, and B3, with varying depth of the cross section as well as few other geometric parameters. I have considered 2.25 meter span for all these three types of beams. Here is the typical loading as well as boundary condition. On the one end, This is no, the, general simply supported boundary condition, where on the one end I have restrained the translation in all three directions. However, rotation is restrained along the longitudinal direction to avoid the complete rotation of the member. On the other end, only two direction the translation was restrained. The 4-point loading setup was used with here is the typical bending moment diagram achieved through this type of loading. Now, coming down to the parameters what I have taken for these parametric studies, the fire time relation was taken by ISO 834 fire curve. The material properties such as yield strength, ultimate strength, modulus of elasticity, and constant Poisson ratio was whole. These material properties were taken from Kankan and Run work of 2012. The steel undergoes large amount of material deterioration. For that, to account that effect, material reduction factors were taken from Eurocode 3 part 1.2. To model the stress strain relationship, I have used Ramberg-Osgood model with the parameters eta and beta suggested by again Kankan and principle of 2011. Now, cold form steel are very much susceptible to the imperfections due to improper handling as well as transportation or the fabrication. To account those, I have taken effects of local distortional or the global imperfection from again from the literature. Now, to consider the temperature on the members, I have considered 5 different thermal profiles. That is ranging from T1, T2, T3, T4, and T5. In all these conditions, the temperature which was exposed on the top and the bottom flanges of the member was different. For example, if we see the T1 thermal profile, here the bottom flange of the member was given the ISO fire curve. However, the top flange of the member is given just 20 degrees Celsius. This is a typical example of how post-cooling, like on one surface there is 20 degrees Celsius, however on the other surface there is heat applied. Second case is the half of the ISO fire is applied on the top flange, so and so forth for the other thermal profiles. There is a typical temperature time relationship what I have used. This is the ISO standard fire curve. This is the half of the ISO fire curve which I implemented in the T2 as well as T4 models. Now, coming down to the results, here is the typical buckle shape of the member I have obtained. This is the typical case of B1 beam, where eigenvalue buckling and basis clearly indicates the presence of lateral torsional buckling. However, T1, T2, T3 till T5 are the different buckle shape obtained from the non-linear analysis. Here the colors red and blue represents, blue is like 20 degrees Celsius and red is the highest temperature whatever imposed on the member. And this is the typical temperature versus vertical displacement curve what I obtained for individual temperature cases as well as for the beam. This is for the case of B1 beam at 50% initial applied load levels. Here, if we see carefully, we will notice that for T5 thermal profile, there is a raise in the deflection, vertical deflection. That is because of the upward bow of the member. However, for the T1, T2 thermal profiles, as you can see, these goes in the downward direction. This is because the bottom flange of the member was heated, which leaded to the downward bow of the members. Here is all the simulation critical temperature once we obtain out of these curves. I have plotted here. Here all these dots represents the critical temperature on the members. And if we see carefully, this is for B1 beam, this is for B2, and this is the B3. That is the most deep beam B3. So if we see carefully for the B1 beam, the lowest critical temperature for higher initially applied load levels, that is, I am talking about this line and this line, was obtained for T5 thermal profile. However, for the other beams, normal depth beams or the higher deep beams, what I obtained, the lowest critical temperature is still governed by the fully heated cross section of the member. So, what are the major reasons behind such type of thing is here. The total deflection of member in thermal as well as mechanical loading is nothing but the combination of thermal deflection as well as mechanical deflection happening due to mechanical loading. The thermal deflection can be broken down by the use of Cook's formula given in 1988. Here, the thermal deflection for bow what is happening depends upon the gradient what is established in the member as well as the length directly. However, it is inversely proportional to the depth of the cross section of the member. Talking about the mechanical deflection happening in the member, this completely depends upon the upcoming load and its nature, location of loading, non-dimensional slenderness, as well as the failure modes involved. For example, here, if we can see, it is the typical example of bottom plane heated member where the deflection is happening downward due to the thermal loading. However, this is the case of T5 thermal profile where the bowing is happening in the upward direction. Another reason for what we have seen in previous case that for the slender section there is like little bit unexpected type of failure is happening because of change in the neutral axis that is happening due to the variation in the variation in the temperature of the cross section. That is once the one side of the member is heated, its material property deteriorates, changes. That is the modulus of elasticity changes and its stiffness changes. That changes its location of neutral axis, which ultimately leads to more unstable systems. So coming down to the results and the final conclusion of my work, this is concluded from this research that the thermal gradient on the member can significantly affect the elevated temperature performance of cold form steel structures, especially flexural members. And a sudden state of collapse has been observed once the compression plane is heated. However, once the tension plane is heated, the failure pattern was little bit gradual. Talking about the tendency of the failure, the members which have bow opposite to the directly applied load fail in a sudden collapse. However, once the bow is in the downward direction, that is with the direction of loading, the failure was little bit predictable. Talking about the future work, more study is needed still to cover a wider range of the affecting parameters to the failure temperature, such as non-dimensional slenderness, depth of the member, length span of the member, mechanical loading, and resistance under development. Thank you.
Any questions?
Thank you.
Is there questions from the
Online or
online now? You introduce the road on your system.
Okay.
Is it on all the flanks? Is it displacement control?
No, sir. This is like force control through FEM simulation. This is the location of the loading. I applied the load on the member. Like once I achieve a particular, suppose 30% or 50% initial required load level, then I stop applying the load. Then the temperature is applied on the member. Like it is.
The displacement under the loading point?
Yeah, this I have measured at the center instead of the loading point. I have measured it at the center of the whole cross section.
Slide 14, when you have displacement measurements, because in T5, you see that we have this properly, so we compare the displacement between different configurations. One of them, we see that displacement change the sign.
Okay.
Yeah, or this is not true. Yeah, this one.
Yeah, this one. Yeah, in this way, what is happening? Once here in this zone, this is when I applied the initial applied load on the member. That's why there is some amount of deflection happening in the member. This is at the 20 degrees Celsius. This whole thing is happening at 20 degrees Celsius. Once I started increasing the temperature, what was happening? For suppose this T5 beam, here the top plane is heated. In this case, the member is going upward direction. That is why, because we are getting such type of behavior. And
Yeah, you get curvature on the
upward bow was happening.
Because we can see this, other steel beams, but in general, as the temperature increases more than 400 degrees, as the motor is changed, the loading, we see just starting from changing the sign of displacement, and after that they go down. This continues practically until failure. Okay. Good. Any comments or questions? If not, this is our last presentation of the day. So thanks to the speakers, thanks to the assistants.